Hello and welcome to the Syft-MS seminar or webinar. My name is Alan and I'll just get right to the PowerPoint. So today we are going to talk about the Syft-MS, which is a fast mass spectromic detection from Sift Technologies. My name is Alan. I work at MSCI as a service technician and an application chemist. I have a master's in analytical chemistry from the University of Copenhagen. MSCI started as an analytical training company in 1998. Then in 2009, we started selling instrumentation such as Gerstle and Agilent. And in 2018, we started collaborating with Sift Technologies. And we offer training courses, instruments, sales and support, as well as application and analysis work in our own labs. Sift Technologies was founded in 2002 out of the ion molecule department of the University of Canterbury in New Zealand. And they now have offices and instruments all around the world. What we'll go through today is what is a Syft-MS, how does it work, what are the benefits and limitations of a Syft-MS. Then we'll try to compare Syft-MS to a GC-MS, and then we'll look at a few applications. So Syft-MS is short for selected ion flow tube mass spectrometry. So we select some ions and react them with our analytes in the flow tube. And then we do MS analysis afterwards. The Sift Technologies Syft-MS instrument is called a Voice 200 Ultra. And it is a direct MS without chromatography first. And that's the reason we can have so fast analysis as we can. The usual advantage when you have direct mass spectrometry is how do you differentiate different compounds, because there are a lot of isobaric compounds. And the way you do it with a Syft-MS is by using ion chemistry. And the major benefit of a Syft-MS is that you have really fast analysis, and it's really good for targeted analysis because you can set up your method so it measures for that. In addition to being a really fast instrument, it also has a high sensitivity and a wide linear range. So you can measure some compounds in the high ppm levels while you measure other compounds in low ppb levels, for instance. But of course, it has some limitations that I'll get into later. The Syft-MS has been underway for a long time. The first model was a university model that weighed more than 5 tons in total. And then when they put this technology into a demo instrument, they founded the company Sift Technologies, which was founded late in 2002. And since then they've just been improving the instruments further. And as you can see in this slide, the main improvement is that it's becoming lighter and lighter. The first Voice 200 Ultra weighed 200 kilograms, and they haven't made a new model, but they have improved this model and taken off another 40 kilograms, which is that they removed the pump because they found a smarter way to get the right pressures in the right places, only using one rough pump. And that's just one of the many things they have improved over the years with this instrument. With a Syft-MS, you can have a lot of different kind of inlets. The kind of default inlet is the high performance inlet to the left, where it's a heated transfer line that you can simply point towards where you want to measure. An example is that we did a demo where a customer wanted to analyze some sawdust, which had been treated in different ways. And we simply did it by, he had some closed containers with sawdust. And then we just took the high performance inlet, drilled a hole into the box, and right after put the high performance inlet in, and then we could get our measurements within seconds. Another way to analyze is, of course, you can use back-end canisters. You can use my favorite one, Gerstle automation. I'm sure that has nothing to do with us being distributors for Gerstle, but it's nice if you want to do static headspace analysis really fast. Another thing that's really nice about this instrument is that you can do breath analysis. It's simply designed that it can handle a high amount of water, which is usually a problem when you run, for instance, GCMS. And then there are some other inlets as well, and these aren't even all the inlets that are available. It's just some I picked out. So, how does a Syft-MS work? A quick overview. In the beginning of the instrument, you have the source region where you generate a microwave plasma from atmospheric air. You have some, in the source region, you make sure that you have the right ratios of each of the components, like you want a certain amount of water in it if you want H3O plus ions and stuff like that. So you make a plasma where it's all combined. Then you have a quadrupole mass filter to select which reagent ion do you actually want to use right now. Then you have the place where the magic happens, the flow tube, where you also inject your sample. And this is where the ions from the plasma reacts with your analyte and thus ionizes the analyte so that it can be controlled by the following quadrupole. And lastly, it's then detected by a particle multiplier. So we'll look a bit more into depth with the different kinds of parts of the instrument. So first off, we have the microwave plasma. And essentially, you pump in atmospheric air at the right pressures, and then you bombard it with microwave energy. Then you, sorry, I just got distracted. Then you bombard it with microwave energy, where you excite the molecules, and then they fall down to the different ions that we are using. Yeah. Next up, in this plasma, you have every of these ions, and we want to select what kind of ions that we react with our analytes. And you do that by having a quadrupole right after the plasma before the flow tube. And then you can very fast switch between the kind of analyte ions you want to use. Another thing I forgot to mention about the plasma is that this is just when you run it in positive ion mode. You can also run it in negative ion mode. And then that means that you have even more options. But generally, more than 90% of any analytical question you have can be solved by using a positive mode. So it's for special applications that you might want to use negative mode. And then we have the flow tube where, as I said, the sample is injected and then it reacts with the ions from the plasma and thus ionize and make the product ions that we then measure afterwards. As you can see on the picture, the carrier gas inlet, because there is a carrier gas for this, there are two ways to control ions, two main ways. Either you can have a gas flow or you can use electricity, electromagnetism to control it. And in this part, it's controlled by a carrier gas. And we'll get into why that is a bit later. But as you can see in the picture, the carrier gas inlet is before the sample inlet, and that's on purpose because then you can take some of the ion energy out of the plasma ions before they react with the sample. Then when they react with the sample, there are some different kind of mechanisms that it can react with. And this is the reason why we want to have this plasma. Because if you have isobaric compounds that have different functional groups, then they will do different kinds of reactions. For instance, proton transfer, that happens to most of the analytes that we're interested in, while maybe hydride abstraction only happens to some of the compounds. And here's a bit of an overview of which different ions you react with that does the different kind of reactions. And again, this is only for the positive mode. There are also, the table is way bigger, but since you can solve most of your analytical problems with positive mode, I'm only focusing on this part to keep it shorter. So the first reaction mechanism is proton transfer, and that is essentially that you have your H3O+, which is protonated water, of course, and then if your analyte has a higher proton affinity than water, which has a proton affinity of 691 kilojoule per mole, then the excess hydrogen would rather be with your analyte, and then we ionize it like that. Here's an example with acetone. You have protonated water, acetone, and then you protonate the acetone and find it at a mass over charge of 1 more because you have the extra hydrogen, and then you just have water as the excess. And since water is neutral, it won't go through the second quadrupole. And another thing that can happen is that, for instance, here with isopropanol, you have an alcohol group, and then when you protonate it, you split off the alcohol group and hydroxy group, and then you have 2 water and find your new product at the mass to charge ratios at -17, because you add 1 and subtract 18. And the most common reagent ion for this reaction is the H3O+. And whenever there is a collision with H3O+ and an analyte that has a high proton affinity, then there will be a reaction. This reaction will occur. So it has a 100% probability. The next reaction mechanism that we have is electron transfer. And that's normal for NO+ and O2+. And that is if the ionization energy of the product, the analyte, is lower than that of the reagent, reagent ion. And the most common reagent ions, as I mentioned, is NO+ and O2+. And opposite of what the proton transfer, here we don't have a 100% probability of the reaction happening in a collision. And that's, of course, important, because if you have a very low probability, then it will also affect your sensitivity. And here we again have some examples where we have the O2+ that really wants an electron, so it takes an electron from the benzene, and then benzene is ionized. And the same thing can happen with vanillin. Now, of course, electron transfer, that can happen with so high energy that the analyte will simply break. So you have your reagent ion and your analyte, and then you get several different fragments. And as I said, this is caused by excess energy during the electron transfer. And this is actually the reason why we use both NO+ and O2+, because they have different ionization energies. And we'll just go through this example before we go to the next slide. If you have butane, then it will lose a methyl group, and then you will see it at 43. And the same with diacetyl, then it will break in the middle, and you can see it at 43 as well. And of course, with some other reagent ions, then you can get different reactions, and then you can differentiate them anyway. For instance, if you used hydrogen transfer H3O+, then you could differentiate these compounds. But since we don't have chromatography, we look at everything we have at the same time. And for this reason, we want to have as few mass peaks per compound as possible. But sometimes we also need to be able to differentiate. So we want a soft ionization, but we want to be able to control that now we want to fragment something. And this is where the difference of ionization energy between O2+ and NO+ comes in. Because as you can see in the example to the right, if we take paraxylene, if we use NO+, that has lower ionization energy, it's of course first ionization energy, then you only get one peak. But if you have another compound here that you're not really interested in, but you want to be able to detect xylene, then you can use O2+ instead and detect it here at the lower mass. And since O2+ has high ionization energy, it's more likely to generate fragmentation. And as I mentioned, we want as few peaks as possible because we want as clean mass spectra as possible because we don't have the chromatography for separation. So if we ionize with electron ionization that use 70 electron volt, then we would get a lot of fragmentation. And if we have, let's say, 5 compounds at approximately 100 mass over charge, if we fragment that a lot, then it will be really hard to see what comes from which compound. That's why we want lower ionization energy. And as you can see in the middle diagram, this is the energy distribution of the ionization ions. And if we don't cool it, we have a large spread, which means that there is a bigger chance of some of the ions fragmenting than others. But if we cool it, then we have a very narrow spread and it's much more controlled. And it's ultra soft because, as I mentioned, electron ionization has 70 electron volts and this is less than 0.11 electron volt. And then how do we cool it? We cool it with our carrier gas. And that's the reason that the carrier gas is before the sample inlet. Because then the high energy reagent ions collide with the inert carrier gas, which is nitrogen or helium. And it doesn't react because it's inert. So that means that it gives a lot of energy to the carrier gas, but remains the same ion. And then we get a much more controlled ionization. Now, another reaction mechanism is hydride abstraction, where we have our NO+ that takes a hydride from the reagent ion. No, not the reagent ion, the analyte. And that's commonly for NO+. Oops, sorry. Again, not every ion molecule collision causes this reaction. Essentially, it's only the proton transfer that has a 100% probability. And now, this kind of reaction, it's characteristic for aldehydes, alcohols, and branched alkanes. Aldehydes and alcohols, they have easily accessible hydrogen that the NO+ can take, and the branched alkanes, they are good at stabilizing when you take the hydride, for instance, the one shown here in isobutane. Then you have all these methyl groups that can stabilize it. and that makes it possible. Yeah. The last reaction mechanism we can use is association. So we are making an adduct where it simply, for instance, the NO plus goes on the analyte, and then we find it at plus 30. And for this to be possible, we need another molecule that can carry away the excess energy, which is also an advantage because we use carrier gas. So we have the carrier gas that can take the excess energy, allowing this to happen. And again, this is characteristic for acid ketones and unsaturated hydrocarbons. So again, this only happens when you have certain functional groups, which means that you can differentiate isobaric compounds based on their functional groups. And here we have a bit of an overview of the different reaction mechanisms. And what you can see is that here at the bottom, for instance, when you use proton transfer, you find it at +1 or -17. Electron transfer, you find at the same mass. Dissociative electron transfer, you find at lower masses, depending on how you fragment your analyte. And hydride abstraction, you also find at -1. And association, you find at +30. So this way we can take isobaric compounds and differentiate them by simply giving them different masses based on their chemical properties. And here we have another example of how this works. So we have acetone and propanol that has a mass over charge of 58. And if you, for instance, react it with H3O+, you will find both at 59. So that's no good. But then if we react it with NO+ instead, then you can see we find the acetone as an adduct, which is at 88, while we get hydride abstraction from propanol, and then we find it at 57. And of course, when you're running the instrument, you can tell it to both run at H3O+, NO+, and O2+. Then it simply cycles through all of them. And as you know, a quadrupole is really fast, so it cycles through them within seconds. Another example, when we have 3 compounds, 3-methylbutanol, 2-pentanone, and diacetyl. They all have a molar mass of 86. So if we just had a normal single quad MS, we would find them all at the same mass. But if we then react them with, if we use a Sift, use H3O+, we won't be able to differentiate them. If we use O2+, you can see as well, they are at the same masses, so we can't differentiate them. However, with NO+, we get some different reactions for each compound. So we have 3-methylbutanol, that's an aldehyde, that was hydride abstraction, so we find it at 1 mass over charge less. We have diacetyl that just have electron transfer, and we can see it's actually dissociative electron transfer. We also find it at 43. And then we have 2-pentanone that has adduct formation that we'll find at 116. And that way we can find all 3, we can quantify all 3 compounds in one measurement, and we'll do this all at the same time. Lastly, of course, to be able to detect the neo-analyte ions we make, we need a quadrupole and a particle multiplier, just like any other MS. In addition to this, the Syft-MS can semi-quantitate just based on its internal calibration. As you can see in this down here, we have the analyte concentration, is the instrument calibration factor multiplied by the product ions, reagent, divided by the reagent ions, which is multiplied by the rate constant. So if we want to quantify, of course, we can always make a calibration curve. And if you want really accurate and precise results, the best way to go is a calibration curve. But if you are comparing different batches, then you might have such big differences that it doesn't matter that you have a good bit of variation, maybe 20 to 30%, and then you can use the internal calibration instead. And the reaction is, here we have, that's the reagent ion plus the analyte, gives the product ion, and we have the rate constant and the reaction time. So we have this equation again that was in the picture. Then we'll just write it out a bit, because this instrument calibration factor, is actually split in a few things. It's the instrument calibration factor for the product and for the reagent, and the reaction time. And if you see here, we have a library that has about 1,000 analytes of the most normal, which has the rate constant and the branching ratio. So when you have dissociative electron transfer, it splits at the same way every time. So you can say that you get 20% of the lower ion and 80% of the higher ion. And you can put this into your library and you can add your own compounds. Just to add your own compounds, you just need to know the concentration of the standard you're running. In addition to that, when we turn on the instrument, we do a validation. And during this validation, it recalculates the transmission function, the instrument calibration function, the reaction time, and the sample flow. And once we know all this, then we have everything in this equation except for the red ones. And that's what we measure when we then run our samples. We always measure our reagent ions as well as the product ion, because then we can do all this. And our reagent ions, we always have an excess of reagent ions, which means that this is operated as pseudo first order kinetics, because it only depends on the concentration of your analyte. And then you can calculate the concentrations based on this, and it's calculated in volume-based units. Now, a big problem with mass spectrometry that doesn't have chromatography before it is that you can have interferences. So how does a Syft-MS handle this? Simply, if you have interferences, this means that some of your ions will have a higher signal that comes from another compound. If you have measurements of the same compound, you can't suddenly have less because of some interference, at least not when it's in gas phase. So this means that the lowest concentration is probably the right one. Then you can set tolerance levels. Because for instance here, we have measured for benzene with NO+, O2+, and H3O+. We have set a tolerance level of 20%, that's the default. And as we can see, let's see, H3O+ and O2+ signals, they are above the NO+ signal by more than 20%. This means that it assumes that these are higher because of an interference, and it reports the lowest one, the NO+ signal. If they had been within the limits, if we had put a tolerance level of 30%, then it would report the average of all of the signals. But if any measurements are outside, the lowest is reported. And actually, this is ppb, but it's actually ppb per volume. Now, all this extra fancy stuff about that we have plasma and stuff like that before, it just means it's the way that we do it. When you work with it, it's just another detector. You can see here we have a GC chromatogram from some Pepsi analysis. You get a chromatogram, you integrate it, and as usual. In a Sift, the Siftogram looks a bit different. You have your injection. You have your injection where you can see each line is actually a compound or an ion. So if you're measuring ethanol with both H3O+, NO+, and O2+, it will be a line each. So here you have a peak equals a compound, and here you have a line equals a compound. And other interest, just before I move on, and the data you get out, you can just plot into Excel and get as Excel reports instead of having to work with it in other software. You can also do some data manipulation within the LabSift software, but mainly you take the data out and work with it in, for instance, Excel or another program. Another interesting thing about this is if you look at the timescales for these pictures. The timescales on the left side is time in seconds. So you can see there's no signal, no signal. That's because I started the injection at 25 seconds. Then had an injection for 30 seconds, and then had it measuring up to 100 seconds, just to have some background values as well. Here, we have a time scale of more than 19 minutes. So this analysis took less than 2 minutes. This took 20 minutes. Of course, one thing is that you can select what compound you look at, but it's still an MS. So you can also just tell it to go in scan mode. And this means that you can just tell it to record all masses. Even if you don't know what you're looking for, you can record for everything. And the wonderful thing is then, if you then later find out that, I want to analyze this data for benzene, then you can make a method and reanalyze the data you recorded in scan for benzene. In addition to that, there is a part in the LabSift software where you can come with guesses for what it is, and it comes with probabilities. So it looks at the data, then you click on the different mass spectra peaks, and then it comes with suggestions. What could this be based on what other peaks we have, and what's the probability that it is this? And usually, if you work with scan data, you can also use other things like chemometrics to analyze your data. This is, I did a measurement in atmospheric air, and you can see here that somewhere around the measurement number 100, you started getting a higher signal of something, 43. That's a pretty generic ion, so I'm not sure what it was, but we could see it and then analyze for what it could be later. Where other data, as you can see here, it's pretty, either there's not much signal or it's just the same noise all the way through. Now, I've talked about how great it is, and I'll just come with some bullet points about it. First off, real-time and high throughput. You could do a full analysis in 30 seconds, and you can actually also do it faster. just depends what you're doing. You get high sensitivity and wide linear range. It's great for small molecule analysis. And the way you can get it selective is via different reagent ions. There are low on-site requirements. And what do I mean by this? Well, you can drive the instrument into a room. All you need is a power supply. Everyone has that. It's just a power plug. And a bottle of nitrogen and the calibration gas for the instrument. And it's a MS that is really fast at starting up. Normally, when you start up a single quad MS, you say that, okay, you shouldn't start measuring before the next day or after at least a few hours. Here, it's normal that you start it up and can run your first sample within half an hour. But of course, there's a saying, the perfect analytical instrument haven't been invented yet and probably never will be. And this is no exception. Of course, there are some limitations to this technology as well. The first one is reagent ion depletion. Then you can have interferences, as I've talked about, and it can be really complicated to work with the non-target data if you don't know what you're looking for. So what do I mean by reagent ion depletion? So in the plasma, we generate a limited amount of ions that we send through the first quadrupole. And as I mentioned earlier, we assume pseudo first order kinetics because normally we have less analyte than we have these reagent ions. And I'll explain this. If you look in the top left corner, this is the injection that I've done. Then we look at some different scenarios. First off, if we inject something at a low concentration, there's no depletion at all. That means that maybe if we have 4.5 million ions, or counts, it says it's counts, so it's not exactly ions, but it's the ratio. So we have 4.5 million, I'll call them ions, from the plasma. And then you react with, let's say, 10,000, 50,000 analyte ions. Then it won't have any effect on how many of the reagent ions are used because it's such a big number difference. But of course, as you increase the concentration, up in the top right corner, we can see now we actually get a little dip in the concentration of reagent ions. And that's just because now we use a kind of significant part of the reagent ions that we have. And a rule of thumb is that the depletion should be less than 20 to 30%. So this is actually fine. We can still use the internal calibration. But down here, if we, for instance, analyze a beer, then it has 5 to 6% alcohol, ethanol to be specific, and that is a huge amount of ethanol, and that will react with all the ions. And because of this, then you will get severe depletion. But what you can do then, if you have the sensitivity for it, which you usually do, then you can dilute it and then run the analysis again, because then you won't have all that ethanol to interfere in this example. But here you could still quantify, then you just need a calibration curve. Strange. Oh well. 1 second. Apparently I didn't include some slides for interferences, but as I mentioned, if you have some compounds that have the same ions, then you can get interferences from other ions. And the Syft-MS does what it can, but sometimes there are simply compounds that are so identical that you can't differentiate them. For instance, I mentioned earlier analysis of wood chips, sawdust, and we could use the Syft-MS to tell the total amount of terpenes. But terpenes are so identical that it's not possible to tell which ones it is. And for that, you would then need GC-MS analysis, which we also did in this case. Now I'll try to compare the Syft-MS to GC-MS. I made some static headspace methods, and the first one you can see here, we take from the tray. This is a window from the Gerstle software. So we take the sample from the tray and we do the analysis. Now in the next picture, I'm just showing what's different from the method I showed before for each different one. And here we can see, here I have a slow injection when using the Syft compared to a fast injection when using GC. And that's just because of the way that it works. Because for GC, you want a fast injection so you can start the chromatography. For Syft, your injection time is actually also your analysis time. So when you're done with the injection, you're also done with the analysis. So here I set it a bit high. I did a runtime of 1.5 minutes. So a full analysis of, I think it's 98 samples, would take 4 hours and 40 minutes. While for a GC-MS, it would take 23 hours. Simply because the GC run is so much slower. But normally we don't do static headspace without first incubating the sample. So I added the agitator, so you agitate the sample. And for the GC-MS, it's approximately the same because then the agitation time is within the GC run, so it doesn't really affect the time. But still, even though it highly affects the Syft time, it's still only 7 hours compared to the 23.5 hours for a GC-MS. So you can still get really fast analysis done. And now I'll just go through a few quick applications. They are actually a bit old now because next week there's a Syft user meeting where they will present some new data. So this is other people who have done some research that I found really interesting. And the first one is a place in China at a primary school where they were right next to an industrial area and they wanted to check the air pollution. So what they did was place a Syft-MS outside of the school. And in addition to that, they placed thermal desorption tubes. So they ran the Syft-MS in scan mode, and they didn't know what they were looking for. Then they ran thermal desorption on the desorption tubes, where they then found out, okay, we can see all these compounds that was during this day. Then they reanalyzed the scan data for these compounds, and then they got this time-resolved peaks. So they can see, like, here we have some spikes of methanol and stuff like that. It's this time resolution that is one of the great advantages of a Syft-MS. Another thing is that it's a really nice and robust instrument, and actually some people, like the University of York and KIOST, which is an institute in Korea, they are actually driving around doing online measurements using a Syft-MS. So they put it in the truck and then put the high performance inlet outside of the truck and then do some measurements. And that's possible because it is so robust and kind of easy to handle. It's still 160 kilograms, but once you have it in the car, it actually works. So you're running a mass spectrometer while driving in a car. And here we can see some measurements from KIOST, where they looked at the harbor town, where they did measurements and found out, okay, these are the areas where we had high levels of benzene. And then afterwards, you can use that data to, okay, can we do something here to improve the air quality? Another example is the University of York. And I'll just mention a fun little side note, which is they again ran around with a measurement every 2.5 seconds. They drove around in the car, measuring, and did a lot of really good work. And in addition to that, they found a funny little thing, a really high level of acetone up at this street. And apparently that was because that's where there was a nail salon. So they drove past a nail salon and saw that, okay, there's a lot of acetone outside of a nail salon, which makes sense. I'm actually a bit out of time. Another way you can use it is for multiple headspace extraction. You can always do a calibration curve, but if you have a really annoying matrix, then you might not be able to. And then you can do multiple headspace extraction. You can also do this on GC-MS. And here you can see there's done different measurements where it exponentially decreases how much you find. Then you can use the right equation and find the right concentration. This is something the company Anatune did. And yeah, we'll skip this one. And then when you do multiple headspace extractions, you are analyzing the same sample again and again. And the estimate, and doing one sample takes about 2 hours, but doing 4 samples takes about 2 hours as well, because they can overlap. And this would take way longer with the GC-MS. Yeah, I'll quickly mention this. This is more to tell about how great the Gerstle is, because they did an analysis with a Syft-MS using a Gerstle autosampler, and they did BTEX analysis of soil samples. And the great thing about this is, okay, measuring 2 grams of soil, you have to do that manually. Making a sodium chloride, saturated sodium chloride solution, you also have to do that manually and put it in vials. But other than that, you can have your Gerstle autosampler add 6 milliliters of methanol, it can do that. Sonicated, it can do that. Centrifuge, that's also possible. Take 250 microliters of methanol and add it to the solution. It can do that as well. It can incubate, and then you can measure the headspace. So most of this analysis can be automated, which I think is really great. And the reason you don't get the reagent ion depletions from this analysis is that when you use NO+, methanol has a lower reaction rate, so that's why you can use it as a solvent without messing up the analysis. And Anatune, they also showed how they got good data, but unfortunately, I'm out of time for this if we also want some time for some questions. So yeah, as a summary, real-time and high throughput analysis, high sensitivity and wide linear range. Great for a simple small molecule analysis. Selective ion analysis via different reagent ions, low on-site requirements, and it's fast at starting up. And thank you for your attention. And if you have any questions, you are very welcome to write me at this email address. And essentially, this presentation is that in addition to working with the instrument, I've seen 1 million webinars on the Syft homepage, which are approximately 1 hour for each of the single parts I've taken. So it really goes into depth. So if you want some really in-depth webinars, then you can go here and find them.